Hello everyone. And
Do you need a mic?
no,
Oh,
uh, my name's Weihan from Xi'an Jiaotong University of China, and the title of my presentation is Numerical Simulations of Hydrogen Enrichment in Weld Joint of L245 steel pipelines. This work is done together with my co-authors from universities and industry who are working on pipeline design and safety. Here is the outline of my presentation. First, I will briefly introduce the background and the motivation of this work. Second, I will show the experiments on the material properties and the residual stress in the L245 pipe welds. Third, I will describe the numerical modes used for the welding process and for hydrogen diffusion. Then I will present the main results and discuss how residual stress influence hydrogen enrichment. Finally, I will summarize the conclusions and give some ideas for future work. Hydrogen pipelines are an important option for long-distance hydrogen transport. They can carry a large amount of hydrogen at a relatively low cost, so they are expected to be a key part of future hydrogen enriched energy system. However, hydrogen can also cause serious material problems. Hydrogen atoms may enter the pipeline still reduce its ductility and lead to hydrogen embrittlement and hydrogen-induced cracking. If these problems are not properly controlled, they may eventually cause damage or even failure of the pipelines. Weld joints are usually the weakest locations in a pipeline system. Circumferential welds introduce complex and high residual stress, which can promote local hydrogen enrichment and increase the risk of cracking. Next, I introduce the experiments on material and residual stress. We use L245 pipeline steel samples taken from circumferential welds. Strain gauges are arranged around the weld region on the outer surface of the pipe so that we can measure residual stress at a different distance from the weld center. For residual stress measurement, we adopt the hole drilling method. According to the standard GBT 31010 2014, a strain gauge rosette is bonded on the pipe surface, and then a shallow blind hole is drilling at the center of the rosette. As the material around the hole is partially relieved, the change of the strain is in the gauges are recorded and converting to circumferential and extra residual stress. The result shows a clear trend. As the distance from the weld center increase, the residual stress first increases, then decreases, and finally leaves off in the far fields. These experimental data are later used to validate our numerical simulation. And I'll turn to the numerical models, starting with the material data and the overall technical route. First, the chemical composition of L245 pipeline steels is measured, including elements such as carbon, manganese, silicons, and other elements. Their mass fractions are given in the table on this slide. Second, we obtain the temperature-dependent material properties of L245 steel, such as elastic modulus, yield strength, and some other physical parameters at different temperatures. These properties are used directly as input data for the welding and the diffusion simulation. Third is the technical route of the modeling. Sorry. Third, the technical route of the modeling consists of three steps. Step 1 is the thermomechanical welding simulation, which provides the residual stress field and the hydrostatic stress field. Step 2 is the hydrogen diffusion simulation, which is coupled with the hydrostatic stress field. Step 3 is the analysis of hydrogen enrichment with and without hydrostatic stress. Finally, the groove design and the pipeline model shown here define the geometry used in the finite element analysis. This slide shows the mesh and the welding process simulation. We built an overall finite element mesh for the pipe and the weld. The mesh is refined near the weld channel, where the gradients of the temperature and stress are high and become closer away from the weld. The main geometry and modeling parameters are listed here. The pipe diameter is 610 millimeters, and the weld thickness is 15.9 millimeters. The design internal pressure is 4 megapascal. The weld is deposited in 6 layers and 7 passes, with weld metal thickness of 2 to 3 millimeters per layer. In total, there are 52,000 elements and 239 analysis steps, including one initializing step and 238 activation steps for the weld passes. To accurately simulate the actual welding process, we employ the element birth and death technique to model the filling of the welded material. From this analysis, the transient welding temperature field is obtained and then used in the subsequent mechanical and hydrogen diffusion simulation. And now I show the main residual stress and hydrostatic stress result. First, we look at the circumferential residual stress near the weld. The counter plot and stress profile along the outer surface show high tensile circumferential stress in the weld region, and the stress decrease gradually away from the weld. The comparison of experimental and the simulated values indicate that the simulated stress profile agrees well with the measured one. The peak position and the peak residual stress from the model coincide with those obtained from the hole drilling test, and the trend of the residual stress distribution are similar. This agreement verifies the reliability of our welding finite element mechanical simulation procedure. We then analyze the hydrostatic stress along two character paths, P1 and P2. Along path P1, which goes through the thickness of pipe, the hydrogen stress exhibits a fluctuating distribution with a peak followed by a valley. Along path P2, which follows the weld direction, the hydrostatic stress generally increase and then decrease. The maximum hydrostatic stress is located at the fifth weld pass on the weld central plane, where paths P1 and P2 intersect. This region will be shown to be the main hydrogen enrichment zone. We now turn to the hydrogen diffusion results. First, we can say that a distribution of hydrostatic stress near the weld is very similar to the distribution of hydrogen concentration. Hydrogen clearly accumulates in the region where the hydrostatic stress is high, especially around the fifth weld pass. This confirms that welding-induced hydrostatic stress is a main driving force for hydrogen accumulation inside the pipeline. Second, the calculation shows that changing the welding speed can modify the residual stress distribution, because residual stress affects hydrogen diffusion. Different welding parameters may also change the patterns of hydrogen enrichment. This suggests that optimizing the welding process can be an effective method to control hydrogen-related damage. Before closing, I briefly summarize the main conclusion and future work. The main conclusions are as follows. First, the coupled welding and hydrogen diffusion models have been successfully developed for L245 pipeline welds. Second, the residual stress predicted by the welding simulation agree well with the hole drilling measurements and the maximum circumferential and extra stress occur at the fifth weld pass. Third, when the hydrostatic stress is taken into account, hydrogen enrichment clearly appears at the fifth weld layer. Finally, the welding-induced hydrostatic stress is identified as a main driving force for hydrogen accumulation in the weld joint. For future work, we plan to include microstructure difference and hydrogen trapping into the model. We also intend to study different welding procedure and post-weld treatments to reduce residual stress and hydrogen enrichment and to apply this modeling framework to other steels and operating conditions. And thank you for your attention. I would be happy to answer any questions. Thank you.